Well, good morning, everybody. Thank you very much for inviting me to give this talk today. It's a very brief, but hopefully inspiring overview of the many things that we're doing at the European Space Agency in our science and our robotic and human exploration programs. And so let's start by just going back almost 60 years to the flight of the first humans into space, Yuri Gagarin, in April 1961, followed a couple of years later by Valentina Tereshkova of the Soviet Union. And of course, the world has changed enormously politically since then. And the powers that were in the original space race, of course, have subsequently come together. And we have now developed with Europe, with the United States, with Russia, with Canada, and with Japan, the International Space Station, which has now had permanent astronaut occupation for more than 20 years. That anniversary celebrated very recently. And unlike the original capsules, of course, we have astronauts now in a shirt sleeves environment, able to enjoy views down on the Earth. This is Samantha Cristoforetti, one of our ESA astronauts. But of course, more importantly, internally doing scientific experiments. This is Luca Palmitano running an experiment called BioRock, which is looking at the ways in which gravity can affect the way that biology and mineral material interact. So looking at how that might be on Mars or places where with different gravity to the Earth by having a centrifuge on the space station. Now, of course, in the meantime, between Gagarin and where we are today, humans went to the moon, and it is now time to return to the moon. This is a major priority of many of the spacefaring nations. If we rewind to 1969, Buzz Aldrin stood with Neil Armstrong on the surface of the moon for the first time, and we are ready to go back. This is the Orion crew vehicle, a collaboration between NASA and ESA. The shiny bit at the front is the crew part, and the back end is the European service module provided by the European Space Agency. And this will provide transportation for our astronauts across the collaboration to go to this location, the Gateway. So this is the lunar gateway in a highly elliptical orbit around the moon, components for scientific labs, for logistics, for refueling, and under the current configuration for going down to the surface of the moon and hopefully staying there longer than we did in 1969 to 1972. So we've now placed the first contracts for the European components. There is a lot of movement towards building the gateway and getting it going. And of course, at the same time, because we're supplying the service module and components of the gateway, we now have a guarantee of 3 European astronauts traveling to the gateway in this decade. Now, why do we want to go back to the moon? There are many reasons, partly as a stepping stone to Mars, which I'll come to at the end of my talk. There's also very interesting science to be looked at on the moon. And one of the locations which everybody's very interested in is the South Pole. So the Chinese mission Chang'e 5 just landed to bring samples back in the last couple of days. And the next mission, Chang'e 6, may go to the South Pole. Why the South Pole? Because there are deeply shadowed craters there that never see sunlight. And there could be, it is believed that there is ice in those craters, water ice, which of course can be used as a resource for water, but also for oxygen and hydrogen as fuel. So this is a sketch of a potential lunar base near the South Pole, mining from one of those craters. And as scientists, of course, one of the exciting things about the moon is the role that it can play in helping us understand how the solar system formed. With plate tectonics on the Earth and water and wind erosion, we've lost many of the original signs of what the Earth was like 4.5 billion years ago. But the moon has much more information to give us. And that's why bringing rocks back and then sending geologists back to the moon to study it in more detail is so important at this time. Now, the European Space Agency, of course, is interested in things beyond the moon. And at the end of 2018, we launched the Bepi-Colombo mission, which is a collaboration with the Japanese Space Agency, JAXA. And that's a mission going to Mercury. To get to Mercury, it has to execute a very complicated flyby sequence, once at the Earth, twice at Venus, and then 6 times at Mercury itself. And I thought I would play a short video of the very recent flyby at Venus, the first flyby. This is at a relatively large altitude. We will return next August and fly much closer over the clouds of Venus. But I thought I'd play this for you with a little piece of music. Let's see if this works. Of course, the engineering involved in going to a place like Mercury is very, very challenging. Mercury gets up to 450 degrees centigrade on its surface. So that this is the temperature of the inside of a pizza oven. So in order to have a spacecraft function at those temperatures, to be cool on the inside, but rejecting all of the incident solar radiation is an incredible technical challenge, which has been solved for Bepi-Colombo. And also the reason, of course, that we're at Mercury is to study the inner part of the solar system, which is heavily affected by the sun. And so this is just a representation of some data from in the NASA SDO mission, and then we'll zoom out and see the same coronal mass ejection from the SOHO mission, which just yesterday celebrated its 25th anniversary. So it's been operating continuously, staring at the sun, yielding data which is very important for science to understand the interior of the sun through helioseismology, the way that it oscillates, like a ringing like a bell. We can study the interior and see the transport of motion of material inside the sun. But also we're looking at that material from those coronal mass ejections and how that ends up impacting the Earth through things like aurorae interacting with the magnetic field. And to study that in much more detail, we're also now, we've joined with NASA to launch the Solar Orbiter mission. That was launched early this year from Cape Canaveral on a US rocket, and is also now will start executing its flybys using Venus to crank its orbit closer in to the sun, and then at a later period at higher ecliptic latitudes to look down on the poles of the sun with imaging for the first time. So the first results have come out. We're seeing very small flares, for example, on the surface of the sun, which may yield an answer to the so-called coronal heating problem. Why is the corona millions of degrees Kelvin when the surface of the sun is only around 6,000 degrees? Further out in the solar system, of course, we've been exploring things like comets with the very famous Rosetta mission between 2014 and 15. And there's a lot of science still to come from this mission as we try to understand this incredibly complicated object of a ball of fluffy ice and dirt and volatiles, which we of course landed on as well. And we understand the structure of this object much better than we understand any other comet. But we're also interested in going out further in the solar system than even Rosetta went. So in 2022, we'll be launching the JUICE mission, which is going to Jupiter to try to understand the icy moons of Jupiter in particular. So thick ice crust standing over kilometers deep oceans of water, of liquid water. And that's a very important tie in the Jupiter system to things that we're doing in astrophysics to study exoplanets. How does our solar system fit in with planetary systems, of which we've discovered thousands orbiting around other stars distant from the sun? And our first exoplanet mission, dedicated exoplanet mission, was launched at the end of last year, the CHAOPS mission, very small satellite with a very dedicated purpose to measure the radius of exoplanets extremely precisely, and combined with the mass measured other ways, we can understand the density of the exoplanets. And here's the launch of CHAOPS from Kourou just about a year ago with the full sound.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, fin de décollage.
And the first science results from CHAOPS have been published this summer. So soon after the satellite was launched. This is a very hot Jupiter-type object in orbit, very close orbit around an incredibly hot blue star. And we can measure the rotation of the orbit, the orientation of the orbit around the star. It actually orbits over the pole of the star rather than around its equator. And that's just a taster of the data that we'll be getting lots and lots back from CHAOPS. And we have other exoplanet missions being built currently, Plato and recently selected Ariel, to find many more exoplanets and study their atmospheres, planets around other stars. Just today, as we move into the larger galaxy, let's see if I can make the change there. Oh, sorry, the line that just came up there, it was hard for me to see, is that the particular planet there is described in the media as the worst planet in the universe. I think perhaps the Earth might be complaining and asking for a rejudgment on that one but that was a headline which we read. So if we now move out to the larger universe, this is a picture taken from the ground from the European Southern Observatory of the Milky Way. And just today, our Gaia satellite, which was launched in 2013, has released its third data catalog. It's the earlier release of the main catalog. Nearly 2 billion stars, 1.5 billion proper motions, distances, brightnesses, and colors, which is an enormous database for doing galactic archaeology. This is just one example of what you can do. This is the constellation of Orion, extrapolated out now from all the motions that we have over a period of 3 million years. And by zooming out on that kind of movement across the whole Milky Way, we can work out how the Milky Way is evolving. And if we reverse the time, we can actually work out how it was put together in the first place. And on more specific regions, of course, we've been operating the Hubble Space Telescope for over 30 years now, a collaboration with NASA, of course. And for much of that period, we've been planning the successor, the James Webb Space Telescope, which is now just a year away from launch. There are numbers here comparing the observatories and their capabilities, but the size is the main thing. It's a much bigger telescope, but much lighter. It's been built in a completely different way. It all has to be folded up from this massive state that you see here. This is the real observatory in testing in the US, and has to be folded up into an Ariane 5 fairing to be launched next October on Halloween. And just for me, I've been involved for nearly 20 years. One of the key scientific topics that it will address is the birth and evolution of stars and their planetary systems. So this is the Orion Nebula in the visible. By going into the infrared, we can actually strip away much of the gas and dust and see a cluster of stars, brown dwarfs, and planetary mass objects in this region. And we'll be using JWS to see the very smallest, very faintest objects in that region. On the larger scales, we're also building a new telescope called Euclid, which is to study the dark universe, dark matter and dark energy, mysterious substances and forces which actually dominate the evolution of the universe. So Euclid is proceeding extremely well, also for a launch in 2022. And on a longer time scale, we're building the Athena X-ray telescope, as the Athena X-ray telescope and the LISA gravitational wave mission, which will combine in many ways to study black holes and the evolution of black holes. In the last 2 minutes I have, though, let's come all the way back and rewind back to our solar system to talk about Mars briefly, because Mars is a major focus beyond the moon, both scientifically and for possible human exploration. Of course, Mars today is cold, dry, with a very thin atmosphere, but we know in the past it had a lot of water. There were liquid water oceans for extended periods on Mars, and we see that in images taken from our satellites. This is a river delta, the remnant of a river delta in the Eberswalder crater, taken by our ExoMars Trace Gas Orbiter, which has been in orbit since 2016. Now, the Trace Gas Orbiter's main goal, of course, is to look for gases which might indicate the presence of life on Mars, the so-called methane mystery. And recently we've discovered that the traces that we've maybe seen of methane on Mars from previous measurements might actually be down to previously unknown absorption lines of just carbon dioxide, of which there is a lot of in the methane atmosphere. But other missions claim they see methane. TGO hasn't seen it yet, so the mystery is still wide open. But beyond that, in 2022, we will launch the ExoMars rover and the surface platform, a collaboration with Russia, just as the ExoMars Trace Gas Orbiter is, named for Rosalind Franklin, because its real goal is to drill 2 meters down underground beneath the radiative environment, the ionizing radiation and the UV, to see if there's signs of life still on Mars, either in the past or potentially even today. And then the real end goal of all of that, of course, is something we've signed up to with the United States, and that's just passed its recent first hurdle, the Mars Sample Return mission, which the samples will be collected by the Perseverance rover, which should land early next year. We will then take a European rover to the surface, collect those samples, put it into a US rocket, launch them back into orbit around Mars, and then collect them with a European orbiter and bring them back to Earth. An amazingly complex program, but proof, I think, of what we can do in space science and exploration when we put our minds to together and collaborate internationally to achieve the best possible outcomes for all of us. And with that, my clock has run out, and I thank you very much. And now I'm open for questions if I have any, Joanna.
Thank you very much, Mark. You definitely didn't disappoint. That was a fantastic presentation. And as always, brilliant visuals and music to accompany it. Perhaps you could comment on how you find bringing together music and the imagery to actually sort of be able to reach into the next generation and to a wider audience and enable space to have that greater impact.
Well, thank you. Yes, that's something from the outreach perspective that we've done a lot of. A lot of it stemmed from the astronauts when they're on the space station, listening to music, interacting with artists for playlists. But we took that in a different direction with the Rosetta mission, involving some very famous musicians who wrote music for us, including Vangelis, famous for Blade Runner and Chariots of Fire. And you very nicely queued up the fact that my next slide, we probably won't be able to see it, but is a thing that we are running called Space Rocks, which involves scientists and astronauts, engineers, in conversation with musicians and artists and poets and authors and actors. And over the coronavirus lockdown, of course, we haven't been able to stage the big live events that we do for that, but we have been running a live stream called Uplink. And we have one this evening, actually, at 8 o'clock UK time. We're going to be talking to two Canadian science documentary makers who work with us on the Rosetta program. But we've had people from Star Trek and Star Wars and Battlestar Galactica and all sorts, and lots of musicians on the program. So to me personally, it's very important, but it does connect through different synapses, let's say.
Excellent. Well, the questions are now coming in thick and fast, as I was expecting from such a good presentation. So first up is, what are the challenges in collating the data from these instruments?
It's a big deal. And of course, we work with many of the other big science organizations in Europe who are involved in the so-called big data problem. So the Gaia Observatory, as I mentioned, has yielded colossal data sets, which now have to be mined. Firstly, they have to be archived and made publicly available around the world, which they all are. But then they have to be available in such a way that people can delve into them and actually explore and data mine. So there's a lot of work we're doing on developing tools which allow people in the scientific community to explore those data, but also we're very interested in having the general public access our data. And that's true with the Mars missions, with the Rosetta and others. The general public have made a lot out of our data in outreach products that we just haven't got the time to do ourselves. So we are utterly dedicated. It's a requirement that we make our data publicly available.
Excellent. And the next question we've got is, how will all the upcoming exoplanet missions work together and complement each other? And what next for exoplanet science?
Well, our program, KOPS, is a small satellite with a very dedicated purpose of measuring the radius of known planets already. JWST actually plays a role. It will go in and measure the atmospheres of known planets. As the stars move in front of the sun, we can actually measure the gases in the atmosphere of the planet. Then Plato is designed to find planets around nearby stars, which are then accessible for following up with a mission called Ariel, which will then measure their atmosphere. So we actually have a very nice comprehensive program now put together in ESA, all through competition. It wasn't as if we decided to do it, let's build a dedicated exoplanet program, but it's worked out in a very nice way. Now, beyond that, we are consulting with the scientific community on what they would like to see on the time frame of 2050. Now, I will have long retired, but there are lots of young scientists who are looking at a future out on that timescale. 30 years ahead seems like a long way, but I've been involved in JWST for 22 years already. So those are the timescales we need to plan on.
Absolutely. A question from Doug Millard. Can Mark speculate on how the falling costs and miniaturization of space technologies may impact on solar system exploration over the next few decades? And we've got a second question as well after that, which will be the final one. So if you could answer briefly that.
Yeah, well, it is something we're looking at, how to use CubeSats and nanosats, obviously initially in low Earth orbit, but other agencies have already used very small satellites as sort of adjuncts in their missions, putting small landers down on asteroids, using them to monitor the progress of their spacecraft with cameras on board. Something we're looking at and we're very keen to do. And we'll do it with our Comet Interceptor mission, hopefully, which will go to a comet in the future and have little satellite spacecraft on it as well. We've got 20 seconds left, sorry.
Right. And final question regarding the star system that you mentioned when talking about Cheops. How do we know that the planet orbits over the star's pole rather than the equatorial plane?
It has to do with the way you can measure it dynamically, but in this particular case, we can see that the light curve is asymmetric, that as the planet moves in front of the star, it takes away some of the starlight. And then when it comes back out again, that light is restored. And by the curve of the profile of the light that's removed, you can tell that it must be orbiting over the cold part of the equator and then the hotter part of the poles, because this is a very squash star. It's hotter than at the top and colder at the equator.
Brilliant. A very simple explanation and brings us to close right on time. Thank you very much for an inspirational presentation and a very lively Q&A. Hopefully, and sorry to keep all the answers so short, but it was great to get through quite a few of those questions coming in.